All right, and here is another example of using that VIR table, this time to solve a parallel circuit. So you can see that visually this is a parallel circuit. We have 3 different branches, each that has its own resistor. So the setup is identical to a series table. So the VIR table always has VIR at the top. And in this case, we have 3 resistors, so I will make 3 rows, R1, R2, R3, and always end with the total or equivalent resistor. Make my nice little table. And we start by listing whatever information I was provided, which in this case, again, I'm given the voltage of the battery, which is going to go next to my total, because think about it, this entire circuit's run by the battery. So 12 volts will go here. Okay, I'm given my 3 resistors. I'll call them R1, R2, R3. 2 kilo ohms, which is 2,000 ohms. And be careful, because again, in this case, they happen to be identical to one another. They do not always have to be. Okay. And this is kind of where I started with my series circuit, but because I am in parallel, my patterns are going to be a little bit different. So I have 3 resistors. They don't add in parallel, their inverses add. And this is where it gets a little bit gross. So if I add one page, let's see. Okay. So I know that 1 over R total, or R equiv, is going to be 1 over the first resistor, 2,000. Oh my gosh, the zeros do not work well. Over 1 over another 2,000. Plus 1 over another 2,000. So remember, go back to the patterns to see. And I'm sorry, the numbers are so gross. Okay, I'm trying to get R equivalent all by itself. So they all happen to have a common denominator. So that is 2,000. Okay, adding the numerators, we get 3 over 2,000. And a lot of people say, ooh, I'm done. But you are not, because R equivalent is still in the denominator. So to solve, you're going to do your cross multiplication, your butterfly, whatever you call it. So I have 3, R equivalent is going to be equal to 2,000. Okay, isolating that R equivalent, I now have 2,000 over 3, which if I did that correctly, should give me about 666 point, and I'll round 667. And you can round at any point. Just keep it consistent in the table. So I found my total, and notice it's smaller than each individual resistor. Okay, because in parallel, the more resistors you have, the less amount of total resistance you get. Okay, so I don't have anything about currents. I only have 1 voltage, but in parallel, all my voltages are identical. They're the same. So once I had 1, I can simply just fill in the rest because I'm in parallel. Okay. And then to find the currents, well, I know my voltage, I know the resistance over each individual segment. So if I find this, I can do V equals I times R, or current is voltage over resistance. When I take 12 over 2,000, I get 0.006. And again, it just so happens that my resistors are the same. So when I take my voltage over new resistance, it happens to be the same. But remember the pattern for the total current. Okay, in parallel, what I should be able to do is add all my currents together to get the total. So by adding these guys, 0.006 3 times, that should give me 0.018 amps. And here's the fun part. I can check this, okay? Because horizontally, V has to equal I times R. So if my current is 0.018 times resistance, 666.667, I should get 12 volts. And if you try it in your calculator, you actually get that answer. So it works, okay? So if you do this successfully, no matter if you look at the horizontal rows, vertical comments, it should all work out. So that is how you use the VIR table in a parallel circuit.